So right now I would ask Mattina to approach the stage. So Matthew is the CTO of Tilera, and he has spent a considerable number of years designing high-end CPUs and multi-core architectures. Of course, most recently for his current employer, but in a past life also for Intel, working on the Tukwila architecture, if I'm not mistaken, as well as for digital equipment, alpha processors, and even spent some time at Cisco. Is that right?
That's right.
Okay. And today he's going to be talking about the good stuff that Tilera has on offer, architecture and performance of the TILE-Gx8072 Manycore processor. So, Matthew, please.
Thanks, Earl. Right, so I promised not to eat into those extra 15 minutes that we just found, so I'll try to go quickly. So yeah, as Earl mentioned, this talk is on the architecture and performance of the TILE-Gx8072 Manycore processor. This is Tilera's latest and greatest Manycore chip. As you probably surmised from the name, it has 72 cores, and this chip is now sampling. So the agenda for today, I'll give you a sort of 10,000-foot view of the GX72 processor, and I'll talk very briefly about how some of our customers actually use these chips in practice. I will then go a little deeper into the iMesh architecture. The iMesh is sort of at the heart and soul of all of Tilera's processors, and I'll describe that in some detail. And finally, I will give some performance results, actually even TCP performance results, dovetailing with the 3 prior papers, and I'll conclude. Okay, so it's sort of a daunting task to try to describe a multi-billion transistor SoC in one slide, but I figured it would be fun to try to do that. So here we go. So on the diagram here, I have sort of a block diagram of the GX72 processor, and I'm going to sort of highlight some of the main features in the chip. So as I said, at the heart of our processors is this tile array, and the tile array is an array of tiles, as you might have guessed. And the key point of this is that these tiles are all interconnected together with this iMesh uncore that I'll describe in detail. But first, if we look at the tiles. So a tile, what's a tile? A tile is a core. What's the core? Well, the core is basically a 3-wide in-order VLIW processor. L1 caches, L2 caches, TLBs, everything you'd expect to find in a core. Inside the tile also is a 256K 8-way set associative L2 cache. And then last but not least is an iMesh interface that provides that tile with connectivity into the uncore. And that's where most of my time will be spent today talking about. Okay, this processor runs at 1.2 gigahertz. It's fabricated in TSMC's 40 nanometer HBM process, and it has a 75-watt TDP power envelope. We surround this tile array with various IOs and hardware accelerators and DDR controllers. I'm highlighting the most interesting ones now. So one of these accelerators is called the MPIPE, which stands for the Multi-Core Intelligent Packet Processing Engine. So what this is it's a wire speed programmable packet engine, and critically it's also a load balancing engine, right? You have packets coming into this chip, you have 72 cores. Who should work on this packet? Well, you need intelligence to figure that out. That's a hard problem. And this engine provides that, as well as programmable packet parsing, which was mentioned earlier in the Google keynote as a critical feature for next-gen hardware. Okay, so what feeds the MPIPE? Well, what feeds the MPIPE is lots of Ethernet ports. So there's 8 10 gig XOWI ports, as I've highlighted here. These can be provisioned as 32 giggies if you so choose. But basically, these guys feed packets into the MPIPE at high rate. There's 2 mica blocks also on the SoC, and also tying directly into the iMesh, although it doesn't quite look like it from this picture. These mica engines are cryptographic and RSA offload engines. So these provide symmetric and asymmetric crypto, 40 gigs of AES, SHA-1, the alphabet soup of cryptography, as well as 44,000 1K-bit keys per second. And that translates into roughly 7,000 keys with 2K bits, which is the latest standard from the standards body. And it's important to note, too, that these resources, unlike other processors, these hardware acceleration blocks don't consume any in-core resources. So if you're doing cryptography at high rate, your cores are not doing anything, and you can use them to do other useful things. So that's worth noting. Also different from other SoCs in this category or in this class is the fact that there's 32 lanes of SerDes for Ethernet, as I mentioned earlier. There's also 24 lanes dedicated for PCIe. So the SerDes lanes are not muxed. So you can be doing 80 gigs of XOE and at the same time be doing 96 gigs of PCIe. The PCIes can be operated as either an endpoint or root complex mode, and they support SRIOV functionality. Okay, of course, there's on-chip DDR controllers. So there's 4 of these running at 1,600 megatransfers per second, which translates into roughly 50 gigabytes per second of peak read bandwidth. These memory controllers do all the sorts of things you'd expect them to do. They reorder requests to prioritize for open pages, and they support ECC, as do the caches. Okay, I didn't know what animation box to draw for this one, maybe the whole device, but there's a key point here, which is with all this horsepower, many devices like Tilera's processor, they use proprietary programming models. We don't do that. We don't think that's the right model for people. People know P-threads, they know C, they know C++, they know Linux, they know GDB, and that's what our device runs. So it's standard SMP Linux, it's a standard new tool chain. And finally, well, show me the money, right? So this processor actually has the world's highest CoreMark score for a single socket processor. And you can look that up on the CoreMark website. It's around 250,000 core marks. All right. So with that overview, let me spend one slide quickly, kind of a markety type slide, showing you how, sort of a broad taxonomy for how our devices are used by our customers. So I sort of broke this into 2 main categories: the heterogeneous devices that customers build with our chip, and homogeneous devices. And it's pretty much what you'd expect. So in the heterogeneous devices, these customers use the Gx72 or any of the processors in our GX family as a programmable data plane, and they pair that with, say, an x86 processor for the control plane. So this, again, kind of dovetails with the talk this morning on SDN. And some of the devices that typify this approach are ADCs, application delivery controllers, firewalls, server adapter cards like PCIe cards or smart NICs, and devices in this emerging SDN and network function virtualization space. Another class of customers does away with the x86 and runs both the control plane and the data plane on the Tilera, which of course you can do because it is just Linux. It's code ports quite easily to it. So here, right, the GX is the control and data plane, and devices that sort of typify this. Our customers are building single chip VPNs, single chip routers and firewalls, IDS, which is intrusion detection and intrusion prevention systems, appliances running the open source Suricata system, which I'll talk about later and give performance on, and video transcoding bridges like MCUs for telepresence. Okay, right. So with that background, I wanted to go into some more detail about the iMesh itself. So what makes the Gx72 tick? What's at the heart of it? At the heart of it is the iMesh. Now, as I said earlier, we have this notion of a tile. We build a tile that contains the processor core, the L2 cache, and this iMesh interface. And we then array these tiles down in a very regular grid. So what the iMesh is the iMesh is really, it's actually multiple mesh networks, and it's a cache coherence protocol that interconnects together all the on-die elements. So the I/O accelerators that I just mentioned, like the M-pipe and the cryptography, they also tie directly into this mesh network. The DDR controllers tie directly into this mesh network at the perimeter, and they are first-class citizens of this system. So when the M-pipe engine wants to egress a packet, it just extracts that packet directly out of the cache as if it was another core reading address 1000. It's all one big system. And that's kind of what the second bullet says, is that it's a single shared global address space. There's not separate address spaces that the programmer has to worry about for crypto, buffering. It's all one flat address space. Anybody can see anything. Of course, there's also virtual address spaces as well, and TLBs for protection, so you don't step on the OS. As I said, there's direct cache access, so packets, incoming packets from those 10 gig ports that I mentioned are deposited directly into cache, which of course minimizes DDR bandwidth pressure, and packets are extracted directly out of cache when they need to be egressed. And it's fully hardware cache coherent, so hardware keeps track of where all copies of a given cache line are at all times in the system, and make sure that whether it's Core 17 reading address 1000, or packet engine reading address 1000, or the PCIe DMA engine reading address 1000, no matter who's reading address 1000, they get the most up-to-date copy. Software doesn't have to worry about it. It's scalable. Everybody throws around the word scalable. What do I mean by scalable? What I really mean is that as you add tiles to this SoC, as we scaled the device from our 9 tile chip up to our 72 tile chip, we get more bandwidth as we do that. This is different from other topologies, as I'm sure you all know. So a ring, for instance, if you have a ring with 32 nodes on it, and you use that same ring to build a 64 node system, you'll have half the bandwidth per node, because ring bandwidth doesn't scale with node count. A mesh inherently scales with node count. And it's not just the interconnect bandwidth that scales, everything scales. As we add tiles, as I said, you're adding more aggregate cache capacity, you're adding more distributed coherence control, and you're adding more cache bandwidth. So the whole thing scales as you add tiles, not just the interconnect. I said in the first bullet that there's multiple mesh networks. There's actually 3. There's 3 mesh networks, separate physical networks. It's not one big mesh that's virtualized. It's separate mesh networks, and we do that because of the coherence protocol requires 3 different classes of messages to avoid deadlock, right? And these 3 mesh networks are sized differently. So one mesh network carries cache line responses. That's a big fat network. Another network carries invalidate acknowledgements for the coherence protocol. That's a skinnier network. But the fact that I wanted to emphasize is that rather than doing one big mesh that you virtualize, that tends to make the router more complicated, and more complicated usually means slower. So we analyzed this 6 ways to Tuesday, and our analysis pointed us in the direction of separate physical meshes. So with that overview of the iMesh, let's go down to the base layer, so the physical and link layer, and spend a slide on what this really is. So each individual mesh network is essentially a 5x5 crossbar, and it's connecting together the north, east, west, south neighbors and the co-located core at that location in the grid. The wires are all point-to-point, right? So because you connect only to your compass point neighbors, that's short wires, and short wires mean low power. Fast arbiter, right? We have a cycle per hop. So if you move to the core, that's 7 logical steps away. That's 7 processor clock cycles. The mesh network runs at the same clock speed as the core, so 1.2 gigahertz. It's a synchronous domain. Our routing is source-based, so the injector of the the request. Say on a cache miss, the injector of the cache miss determines the route that request will take through the mesh network. It's wormhole routed. We did a lot of work on the route headers, right? Again, going back to this point about fast arbiters and low latency, we hyper decode the route through the network so that the arbiter has very little in the way of gates to figure out what do I do with this incoming packet. We have link level FIFOs, and we do per hop flow control. At each flop, at each hop in the network, a packet can decides whether it can advance based on the depth of that link level FIFO. Going sort of down even further, we follow sort of an ASIC design methodology at Tilera, but we do pockets of custom design where it really matters, where it has impact, right? So this is one area where it has impact. So we do hand-placed layer 7 and layer 8 metal over the L2 cache. So what I mean by that is that these physically, these mesh wires, you need area for them. Well, where they actually fly is over that L2 cache. And so we don't have a dedicated routing channel. You can't look at a floor plan and say, there's the mesh. It routes over the cache array. And that minimizes the area on the chip. And again, a physical design point that matters in practice, right, is the fact that this regular design style, design the heck out of one tile and then array it, n by m times to build whatever size chip you need has a huge amount of advantage for us in terms of time to market, and that makes our customers happy because they know we can proliferate new chips very quickly. Finally, I put in the lower right here, the widths of the different networks, just the link width. So the SDN, the nomenclature is Snoop Dynamic Network, although we don't snoop. RDN is the Request Dynamic or Reply Dynamic Network, and QDN is Request Dynamic Network. As I said, they're sized differently depending on the class of traffic, and I put their bisection bandwidths as well. Whoops. Okay, so I talked about the iMesh as sort of an interconnect technology, but it also implements the sharing and the communication protocols. So let's step back a bit and talk about how caching works. As I said, every tile has private L1I two-way set associative and private L1D caches, also two-way set associative 32K both. So every tile has that, and every tile also has a 256K 8-way set associative L2 cache, all ECC protected. The different thing here from other processors is that L2 cache caches both private L2 lines, in other words, private meaning requested by the co-located core. So core 17, requests a cache line. He installs that line into his L1 and L2 caches. That's fine. It also serves as an aggregate L3 cache. So it could be the case that core 84, if we have an even bigger chip, requests a cache line whose home happens to be at tile 17. In that case, tile 17's L2 cache actually serves as a backing L3 for that cache line that's going to be cached privately at the requesting core's L2. If that's not clear, I'll show a little animation. I'll show a little animation no matter what, even if it is clear. Also, the coherence directory is distributed. So, as I said, the hardware is keeping track of where everything is, and that's also distributed with the caches. So, at every tile, at every L2 bank, there's a coherence directory that knows for lines that have been requested from here who has copies of those lines, and that hardware will also be the thing that invalidates those lines when they become stale. We also implement a flexible cache line distribution scheme. The way to think about this is for a given page of memory, the system, meaning either system software or the user, can specify, like when you do a malloc, you can say, malloc this page, and by the way, I want it on core 23. That's where I want the home to be for that page of memory. If you don't do that, which would be the default, the system will simply spread the cache lines on that page out amongst the entire L2 banks. So line 0 on that page may end up on being home by core 5. Line 1 on that page may end up being home by core 17. It spreads it out in a uniform way. As promised, here's the animation. So I don't know if you can see this, but I have a green tile, a blue tile, and a black tile. And so what I'm going to show here is the green tile is going to do a load of address 23, and it's going to miss in its cache. And the home, it's going to miss in its local caches. And the home for that cache line, that address, is going to happen to be at that blue tile. So it's going to send a request over the iMesh to the blue tile. The blue tile checks his L2 cache, says, by the way, I don't have it either. So he goes and gets it from DDR, and then he ships the copy back to the requester, the green tile, who stores it in his L1 and L2 caches. I actually simplified this. In reality, the DDR controller delivers the copy directly to the green tile and to the home, but I decided to keep it simple. So now that cache line X is present in the green tile and it's present in the blue tile. And I think what's going to happen now, the black tile is going to also request cache line X. He's going to miss. He's going to, of course, send the request to the home. But now everybody's happy because we've already installed that line at the home. And so he ends up doing basically an L3 hit on that cache line, which is good because it's lower latency and it's less DDR bandwidth. Okay, so that's sort of the simple case, right? But things get a little hairy when you have stores and shared copies. Right now it's not so simple of like, we'll just go to the home. So I have a slightly more complex example here for a remote write hit with a share. So what's going to happen here is tile 0 is going to do a store of a virtual address V, and he's going to set it to 1, and it's currently 0. The value of that address is currently 0, and it's currently cached in tile 1 and tile 2. So what happens? Well, he does a store and he goes through the TLB, and he gets the translation for V, which is P. And then he, tile 0, the one who's doing the store, looks up in his cache and says, oh, I actually have that, so I'm going to change it to 1 because it's no longer 0. Then he pushes that write to the home over the SDN network, and this is sort of why we need the 3 channels, 3 separate mesh networks. So he writes that through actually to the home, which is tile 2. Tile 2 is tracking the state of this line because he's the home for it. So he says, oh, that's interesting. I know that tile 1 has a copy of this, so I need to invalidate that copy, right? Else we'd have a coherence problem. So tile 2 fires an invalidate over the QDN to tile 1. Tile 1 does what he's told and throws away the stale copy. And then tile 1 has to tell tile 2 that this has been done. So he sends back an acknowledgement message saying, yeah, I did it. And at that point, tile 2 actually makes the change from 0 to 1, and he tells tile 0 it's done. Now, you might think, well, what's tile 0 doing all this time while this is happening? It looks like a really long time. There's these messages flying around. Tile 0 just keeps executing, right? Because this is a store. No one depends on a store unless you're doing a memory fence. We have a memory model that's a relaxed memory model, so it's not like you do a store and then wait for that to become globally visible. You just do a store and you keep running. So since there's no consumer of a store, there's no need to stop. So while all this is going on, tile 0 is very happily doing multiplies and adds and subtracts, unless he does a memory fence, which is not the common case. And if he does a memory fence, he waits for the acknowledgements. Okay. So then to make my talk more interesting, I decided we should watch some movies. So this is iMesh at the movies. So we develop a lot of tools to simulate the mesh network and the coherence protocols and all that. But But one really kind of fun tool that we made was, it's sort of a simple tool actually. It's a standalone network simulator. So it's a mesh simulator. You tell it, what are the dimensions of the mesh, and then it's parameterizable. So you can say, I want this routing policy. I want these injection rates. I want a Poisson distribution of traffic, or a Poisson injection rate. And so we did all that, and we would run it, and we would get some statistics, and we'd say, oh, that's interesting, and we'd compare different routing algorithms, and that was all good. And then somebody came up with the idea of, well, what if we actually took snapshots from this tool, take the output from this tool, with time, and let's just dump out the queue depth at each location in the mesh. So what I mean by queue depth is, there's this n by n mesh, say, and at each point they're the tile that's there is injecting at some rate, right? And he has a queue to hold onto the things that he's trying to inject. And if he can't inject, those queues back up. And so what we printed out was those queue depths as a function of XY location, so like a 2D table, as a function of time. And then we said, well, what if we actually made a movie out of that? So let's show with time the queue depth as a 2D plot, and let's color it differently depending on the depths of the queues. And so we had one more idea, which is, well, if we want to evaluate different routing algorithms, let's put all 4 movies onto like one display, so we can say round robin arbitration with this particular set of injection rates behaves like this. So at the same time, a different algorithm for routing behaves this way. And then we can sort of look at these 2 or 4, in this case, network simulations evolve with time. And so that's a really long way of saying these are fun movies to look at. But that's what this is. So in the lower left, I've plotted a round-robin arbitration scheme. What we were looking at with this simulation was we have these high-speed network IOs on the left edge of the mesh. They're injecting at a very high rate. And we wanted to know, you have these 2 hot spots on a mesh, right, that are injecting traffic in at the periphery. We want to know what's the effect of that as you ramp the traffic, uniformly distributed traffic between all the other nodes on the mesh. And that's what this is showing. So you get a characteristic dynamic behavior for the round-robin arbitration. The others were variants of a scheme called network priority arbitration, where traffic that's already in the network takes priority over traffic that's trying to be injected into the network. So what these movies help with was sort of building intuition about the dynamic behavior of the mesh. And I just thought they were cool. Okay, finally, I'll discuss some performance results and a summary. So what does all this mean? So at the end of the day, we want kick-ass performance out of our processors at low power. And so what I'm showing here is the scaling behavior of 2 applications that are important for our customers and therefore important to us at Tilera. And these 2 applications that I plotted are TCP throughput and H.264 video encoder. So on the left, I'm showing TCP throughput on the y-axis in terms of gigabits per second, and on the x-axis, I'm showing the core count. So basically, these are measurements on real silicon. We have the GX72, as I said, it's sampling. And what we're doing here is we run a single core running TCP. We run 2 cores, 4 cores, 8 cores, and we measure the performance as we scale up the number of cores. For TCP, and so that's what I plotted there. So for TCP, the x-axis goes from sort of 1 core to 30 cores, and the y-axis tops out at 80 gigabits per second. And we get basically a 30x improvement from 1 core to 30 cores while we do this. And we top out at 80 gigabits per second because that's where this chip is I/O bound. As I said, we have 8 XOWI ports. We've maxed out the I/O at that point. We can't do any better. But you have, the point or the upshot is that, so we're able to do this with 30 cores, linear scaling, and you have 42 cores that can do other tasks, such as deep packet inspection is something that that's important for our customers. Same thing for the adjacent graph, but a different domain. So networking on the left and video on the right. So on the right, we're running a video codec, an H.264 video encode application. And on the y-axis there, I'm plotting frames per second, and again, core count on the x-axis. And here, I ramped the core count from 1 core to 72 cores. And it's not perfect. We get a 65x speed up by doing that. And we end up with, it works out to about 650 frames per second. This is 1080p 30, so that's about 22 streams of 1080p 30 H.264 baseline encode with 72 cores. But the cool thing is that the linear scaling, and the linear scaling is a byproduct of all the stuff that I've been talking about to this point. It's the iMesh, it's the cache bandwidth, it's the scalability of the iMesh uncore. I put 2 other applications I don't show the scaling for, but just to show you their aggregate performance. It's 13 gigabits per second on Suricata, which, as I mentioned, is an intrusion detection system, and packet forwarding, 80 gig on 40 cores. Right. So, yeah. So to summarize, you know, so a couple points I wanted to make. The iMesh, it's not just a mesh network. It's the substrate that provides the tiles and the entire SoC a scalable uncore. So that's the cache coherence protocol, the caching itself, the bandwidth of the aggregate cache. The iMesh is all of those things, and the iMesh is what's enabling our GX family of Manycore processors, of which in this talk I highlighted the GX72. But this is what's enabling our processors to efficiently scale performance from the GX9 all the way up to the 72-core GX72. Thank you.
So do we have any questions?
Yeah, so, well, that depends on the number of connections. So in the particular example I showed, there are 256 connections used. So first question is, to be clear on, is that whether or not it fits in the cache depends on the number of connections. So if you have 1 million connections, the TCB control block aggregate is too big to fit in the cache. So that it's a good question, because often people will cheat and use only a small number of connections, as I've done here. We also do this measurement with a very large number of connections. And initially, it didn't scale well. And so we did a slight modification to the code, which is to insert prefetches. So if you prefetch far enough ahead of time, which is, say, 200 cycles before you need that particular TCB control information, if you insert a prefetch, we're able to get very good scaling, even with, say, millions of connections.
So about the cache coherency protocol, so essentially if the requester is not the owner, then you have your cache footprint, right?
You have your cache footprint?
Yes.
Sometimes.
So you always have 2 lines, right?
Yeah. So sometimes. So there's a couple things to say about that. Generally, that's true. So it's true for pages that are not homed at the requester, right?
Which is most of them, statistically.
It depends. So, you know, so our system does some smart allocation of pages. So it knows, in some cases, where the page should be homed, and it will home it there. In other cases, it doesn't, and in that case, yes, you have your cache allocation. What and everybody sort of that we talked about this highlights this. What we find is that LRU actually, or pseudo LRU algorithm that we use to decide which lines to kick out, does a really good job at deciding which lines are important and which lines are not important. So in spite of the fact that we have this shared hybrid with L2 and L3 lines, we don't seem to incur a cost for that.
Sure. That was the statement. The actual question is,
yeah.
why didn't you use MESA for some other protocol where you only have 1 copy of your cache line that may be owned or shared or something, whatever? Is there a specific reason for this?
1 copy of the cache line. So, you know, You could do that. I think it makes the directory structure a little bit more complicated. So right now our directory is simple. It's coupled to the L2, and it sort of knows where the copies are. I think you could do that. We didn't see an advantage to doing that, I think, is the short answer.
Okay, thanks.
Yeah, hi. Question, in the TCP performance, you show 80 gigabits per second achieved with 1,500 byte packets.
Yeah.
Using, I believe, 30 cores. But the worst case load is when you have minimum size packets.
Yeah.
Which would be about 80 bytes or 64 bytes per
Yeah.
packet. So with that, there'd be about 20 times more packets per second with the minimum size packets than with the maximum size packets. And so would it be correct to guess that the throughput would drop from about 80 gigabits down to 4 gigabits then?
It dropped significantly, but also we have more cores to spare, right? So I showed you the scaling, as you said.
That was with 30 cores, which was half.
Yeah, it was the 30 cores. So, if you are using 100% min-size packets, throughput does drop, and we have that data. We have data, of course, for iMesh and as a function of packet size. The intent of this wasn't to show, what's our performance for min-size TCP, but rather we can scale linearly. And even with 64-byte packets, we still scale linearly. Now, whether or not, I think your question is really, can you do 80 gigabits per second with min-size TCP packets, which is a different question than what I was trying to answer on the slide. I don't actually know the answer to that off the top of my head. But we certainly see a decrease in performance, or rather, you need more cores to achieve high performance as the packet size drops.
My basic question is, how do you do the workload distribution, particularly when you send a package to a tile? First, you have to be reasonable from the capacity point of view. Second thing, that tile must have a computation power available. How do you manage that?
Yeah, so that's part of the magic of the M-pipe, as I mentioned at I think the GX72 at a glance slide. So the M-pipe is sort of the intelligent on-chip NIC, and it's tracking flows, and it's tracking packets per flow. So it knows how many packets are in flight for a particular core. So when it gets a packet for, say, flow 17, the first thing it asks is, are there already packets in flight for this flow? Okay, so if there already are packets in flight for this flow, then it sends the packet to the core that's handling that flow. If there's not packets in flight for that flow, then it's free to redistribute. And that's where it uses this global information that it has about how many packets, basically, are queued for each core in the system. So it's simply done by having knowledge of how many packets are queued for each core.
I have one more question. In your default mode, your pages are distributed across different tile. I assume
I'm sorry, your what?
your page is distributed
Page.
across different tile.
Mm-hmm.
I assume that if you have one package which is bigger than one line, the package will be distributed across tile too.
Mm-hmm.
What is the advantage to do that instead of putting them all in the one tile?
Putting it all in one tile?
Yeah.
If you put it all in one tile, you can create hotspots. Generally speaking, it's better to distribute things across the aggregate cache rather than to try to jam it into one tile. Better in the sense of you get more cache to play with, you get a big pool of cache, and you also get more bandwidth. If you try to drive an entire packet to a single core, well, that's more bandwidth, that's more potential hotspotting at that particular core. So generally, it's better to distribute. I can't hear you. Yeah, you have more iMesh traffic. That's okay.
Hi, this is Keshav from IBM. You made a statement which raised quite a lot of storm of questions in my mind. You said the packets are directly fetched from Xavi into the cache. Now I saw you have 256 byte of cache.
We have 256K of L2 cache per tile. That's 18 megabytes of aggregate L3 cache.
Okay. So now question number one is, if the packet goes directly into the cache, what happens to the associated instructions and data to process that? Where do you fetch it from? That's number one. Number two, if you have limited amount of cache, how many packets can you fit in? Because you have 72 cores, and do you fetch the whole packet or just few bytes? How do you achieve that?
Yeah, so if I take your last thing first, how many bytes? I mean, it depends on the application, right? So if you're doing a DPI application that wants to look at every byte in the packet, then you're going to touch every byte in the packet. If you're doing something that's going to do a flow decision based on the L4 header, then you're not. So then you're going to do a lookup based on the L4 header, which is a few bytes of the packet, and then you're going to egress it, and it's going to be extracted directly out of the cache, and so you've burnt no DRAM. Now, your first point, you said something like, where are the instructions and data to process the packet? The instructions and data are just in the cache. It's just a shared cache. Whatever's hot stays in the cache, and whatever's cold gets kicked out of the cache. Maybe one subtlety to that is that there's L1 caches as well. So perhaps it's the case that the iStream footprint for your packet processing application completely fits in your L1 iCache, in which case it's not using any L2 capacity at all. Or maybe that's not the case. It just doesn't matter, right? A cache is very good at figuring out what to keep on die and what to not keep on die.
Thank you.
Any more questions?
Can you say something about the routing algorithm, deadlock prevention, and congestion avoidance in iMesh?
Yeah, I can say a little bit about that. We actually have multiple routing algorithms in hardware, and they're all sort of well known. The default routing algorithm that we use is network priority arbitration. So what we do is packets that are already in the network take priority over packets trying to inject into the network. And we found that worked best across the application space that we were looking at. Congestion control, we don't do a whole lot for congestion control for inside the iMesh. We do packet pacing on the high-speed IOs to avoid sort of extreme bursts coming in. We also do priority in the DDR controllers. So the DDR controller can be made aware by software that requests from this particular core should be given priority over requests from other cores. Deadlock. So there's two kinds of deadlock. There's routing deadlock and protocol deadlock. We do sort of XY routing, so there's no route deadlock. The protocol deadlock, there's basically 3 channels in the coherence protocol. There's like a request channel, sort of an invalidate channel, and then a response channel. So that's why we have these 3 physical meshes, and they're just separate meshes. Of course, those 3 channels pour back into the microarchitecture all over, right? In the L2 cache, those same channels have to be respected. So when you're, if you fill up your, rob buffers or misrequest buffers with all requests, then you can't process a snoop, you're screwed. So those VCs propagate back into the microarchitecture.
Sure. So Rajan Goel from Cavium. Listening to you, it seems like, to get maximum performance out of your chip, the application or the software needs to be well tuned for knowing your microarchitecture, how the L2 accesses happen, or how L3 is, or what is iMesh, or your M-pipe distribution mechanism is. So my question is, I'm sure, if you tune the application for your chip, you can get 100 gig or whatever it is designed for. But do you run into this problem with your target market? Another argument is that applications are written for x86 without worrying about the architecture. When you migrate to it, you don't get the same performance. So how do you address that with your customers, and do you see it as a problem?
Yeah, I think it's sort of a truism to say, like, tuning the software will get you higher performance. That's always the case on any architecture, x86, Cavium, Tilera. If you tune, you will do better. What we find is that many applications actually, you don't need to do tuning much at all, actually. The M-pipe, if you want to use, a special load balancer mode, that has to be, you have to have some smarts and say, here's how I want to use the load balancer. But a large space of applications, say Hadoop, Java Hadoop, it just runs out of box on our chip very, very well. And why is that? That is because the hardware is provisioned for this, right? It's not a small cache. It's an 18 megabyte L3 cache. If you contrast that with some of our competitors, they have like a 2 megabyte on-chip cache. That's an enormous difference for out-of-the-box performance. Cache matters, right? You're talking about the difference in load latency of 13 cycles, for an L2 or L3 hit versus 200 cycles for a DDR. The iMesh is provisioned for massive amounts of bandwidth. So these sort of bottlenecks that you're talking about when you port applications, many of those we don't hit because the architecture is provisioned to handle that.
Understood, thanks. One related question, sorry. I think you didn't share your instruction set architecture,
yeah.
But in the industry, there is a trend to standardize towards x86 or MIPS or ARM. So do you feel that as a problem with no support from ecosystem for your architecture?
Yeah, so most of our customers don't care. The benefit that they get from using our processors outweighs the ecosystem challenges. And I think that's especially true because it's not a proprietary architecture in the sense of like our own programming model. It's basically C and Linux and a GDB tool chain. So it's the effort required is not different from compiling for a standard MIPS or ARM-based architecture. It's kind of the same thing.
Yeah. For your protocol deadlock avoidance, do you require any pre-allocation or end-to-end flow control?
That's an extremely complicated question. So you're saying, do we require pre-allocation to avoid deadlock in like the cache coherence protocol?
Or end-to-end flow control?
Or end-to-end flow to control. I'm not sure what the last part means, so I'll answer the first part. Yeah, as I said to the gentleman over here who asked the question earlier, the whole microarchitecture has to be aware of these three classes of traffic, right? So we have to give one example, right? We can support 8 outstanding miss requests from the L2 cache, and these chew up some resources in the L2. Those resources may also be used by incoming requests from other cores. If we were to allocate all of those resources for outgoing requests, then no incoming snoops would be processed and the machine would deadlock, right? So we pre-allocate. We say, I wouldn't actually even call it pre-allocate. We just make sure that we always have a resource available for the highest guy in the protocol tree. And I think everybody has to do that.
All right, so this was obviously a very stimulating talk, so thank you very much,
Thank you.
Matthew.
Thank you.